Swayam Prabha. Digital India. Educated India.
Welcome to the lecture series on design of transmission elements. Myself, Dr. Kailash Narayan Pandey, professor in Department of Mechanical Engineering in Motilal Nehru National Institute of Technology, Allahabad, Prayagraj. In this lecture series, we will study about different transmission elements such as gears, then the bearings and belt drive. And in the gear, we will study the design of, first of all, the introduction of gears, and then design of spur gear, design of helical gear, design of bevel gears, then design of worm gears. And in the bearings, we will study the design of sliding contact bearings and then selection design of rolling element bearings. And at the last, we will study the design of belt drives. It will be basically the selection design of belt drives. So, let us start this lecture series with general introduction about the gears. The simplest means of transferring rotary motion from one shaft to another shaft is a pair of rolling cylinders. That means, we have a shaft here and there is another, and we want to transmit power. We have a shaft and we have another shaft, and we want to transmit power from this shaft to this shaft. Then the simplest way is to mount two cylinders like this, and they will be touching each other at this point. They may be external set of rolling cylinders or the internal set of rolling cylinders. In the second diagram, this is an annular ring and this is a disc, and we want to transmit power from one to another. Now, if sufficient friction is available between these two discs, then this mechanism will work quite well. There will be no slip between the cylinders until the maximum available frictional force at the joint is exceeded by the demands of torque transfer. Now, the drawback with this simplest mechanism for transfer of power from one shaft to another shaft is, in this relatively low torque can be transmitted, and that torque will have maximum capacity up to the frictional force which is acting between the two cylinders, and there is possibility of slip. Now, some drives require absolute phasing of the input and output shafts for timing purposes. This requires adding some meshing teeth to the cylinders like this. On the cylinders, some teeth are made, and the teeth of one cylinder is meshing with the another cylinder. They then become gears, and radius of the equivalent cylinder is called the pitch radii. The surfaces of rolling cylinders will become the pitch circles, and their diameters the pitch diameters of the gears. The thing is, this gear is replaced by the cylinders. Let these two cylinders were there, and we are able to transmit power with the help of these two cylinders and with the help of this teethed arrangement equally. Then the cylinder, this cylinder, the surface of this cylinder will be the pitch surface, and the circle formed will be the pitch circle of this gear, and the diameters will be the pitch diameter. This will be called the pitch diameter of this gear system. Gears are toothed members which transmit power or motion between two shafts by meshing without any slip. Hence, gear drives are also called positive drives. In any pair of gears, the smaller one is called the pinion and the larger one is called gear, immaterial of which is driving the other. For example, in this figure, the smaller one, the smaller gear will be called pinion and the bigger one will be called gear, irrespective of which gear is driving or which one is driven. When pinion is driver, it results in step down drive in which the output speed decreases and the torque increases. On the other hand, when the gear is the driver, it results in step up drive where the speed increases, in which the output speed increases and the torque decreases. Now, the fundamental law of gearing. Conceptually, teeth of any shape will prevent gross slip. That means, on the cylinder, you have formed a teeth. Now, teeth of any shape can prevent slippage. If we see the old water powered mills and windmills used, the teeth were merely wooden pegs, you see wooden pegs stuck into the rim of wooden cylinders. So, they were simply wooden pegs and they were engaged with each other, and thus they were transmitting power from this shaft to this shaft without any slippage. But the drawback was there was no possibility of smooth velocity transmission because the geometry of the tooth pegs violated the fundamental law of gearing. In this case, the fundamental law of gearing was not satisfied, and so it was not possible to get a same velocity ratio every time. The angular velocity ratio between the gears of a gear set must remain constant throughout the mesh. So, if we see this gear, let this gear is driving this one, then there must be a constant value of angular velocity ratio. So, if this is rotating with omega 1 speed, then this must always rotate with omega 2 speed. This omega 2 should be fixed, and the ratio omega 1 upon omega 2 must be a fixed quantity. So, if we are getting this one, then we will say that the gear tooth formed is satisfying the fundamental law of gearing. We are getting a uniform, a same or fixed velocity ratio. Then gear sets are said to have conjugate action. The thing is, omega 1 divided by omega 2, omega 1 is the speed of first angular speed of the first gear, and omega 2 is the angular speed of the second gear, which is meshed with the first gear. Then the ratio omega 1 divided by omega 2 must be equal to the n1 divided by n2, where n1 is the RPM of the first gear and n2 is the RPM of the second gear, revolution per minute. d2 is the pitch diameter of the second gear, d2, and d1 is the pitch diameter of the first gear, d1, and z2 is the number of teeth on the second gear, z2, and z1 is the number of teeth on the first gear. Now, this d2 and d1 are a fixed quantity once you have selected a gear, and so this is a fixed ratio, fixed value. This is also a fixed value, and so omega 1 divided by omega 2 will be a fixed quantity. So, if this is satisfied, then we will say that the gear tooth is following the fundamental law of gearing or satisfying the fundamental law of gearing, and there is a conjugate action. So, the terminologies are shown here. The number of teeth are Z on the pinion Z1 and on the gear Z2. Pitch diameters are D1 and D2. Speed are N1 and N2, and the rotational speed in radian per second is omega 1 and omega 2. Now, when one curved surface, let us see, this is the one curved surface, pushes against another, and another curved surface is this one. Now, if one curved surface is pushing the another, then the point of contact, this is the point of contact and this is called C, point of contact C, occurs where two surfaces are tangent to each other. At the point C, these two surfaces are tangent to each other, and so at point C they are at contact, and this is called the point of contact. And the forces at any instant acts along the common normal of these two surfaces at the point of contact. So, if AB, this A, B, this AB line, this AB line is common normal at the point of contact. Point of contact. Okay. So, one curved surface is pushing the another curved surface, and at point C they are tangent to each other, and the forces which are acting from this body A to the body B is along common normal at the point of contact AB. The line AB representing the direction of action of forces which is applied by body A, curved surface A on the curved surface B, and this is called the line of action. This common normal at point of contact is also called the line of action, this one. The line of action will intersect the line of centers. This is the body A and it is rotating about this point O, and this body B which is rotating about this point O. Then the line of centers is this one, OO is the line of center. Now, this line of action is intersecting the line of centers at point P, okay, this point P. The angular velocity ratio between the two arms or the two bodies is inversely proportional to their radii to the point P. That means inversely proportional to OP and this OP. If I say this as OA and this as OB, then the pitch radii will be this RA for the body A, this one, this is the circle passing through P and center at OA, and this is the circular arc passing from pitch point P and center at OB. OB. So, this is the pitch radii RB of this one. So, circles drawn through point P from each center are called pitch circles. This will be the pitch circle. And the radius of each circle is called the pitch radii. RA is the pitch radii of body A and RB is the pitch radii of body B, and point P is called the pitch point. Now, in order to maintain constant velocity ratio between two missing gears, the common normal, this AB, at point of contact must intersect the line joining the center of rotation, OA and OB, OA and OB at a fixed point. Then only this RA and RB will be fixed and you will get a fixed ratio. So, the fundamental law of gearing says that to obtain a fixed velocity ratio, the common normal at the point of contact must intersect the line of centers at a fixed point. So, if you have a cylinder, then you have to make gear teeth with a profile which should satisfy this law, which is called the fundamental law of gearing. Now, there are three profiles which satisfies this fundamental law of gearing. One is called the involute, then another is cycloidal, and the third is circular arc or Novikov. Now, involute tooth profile is formed by, we have a circular disc, and on this circular disc we have wrapped a wire, wire on it, fix. Now, we are unwinding this wire in such a way, we are unwinding this wire like this. Then the locus of this point P will form the involute tooth profile. Well, now this involute tooth profile satisfies the fundamental law of gearing, cycloidal also satisfies the fundamental law of gearing, and the circular arc or Novikov also satisfies the fundamental law of gearing. Now, if we see the involute tooth profile, then let we have a driven gear which is rotating with this center and a driving gear which is rotating with this center. The driving gear is rotating in an anti-clockwise direction, then the driven gear will rotate in a clockwise direction. Now, the involute tooth profile are shown here, this and this one. So, point of contact at any point is this one. This is the point of contact. Okay. Then let the cylinder on which we have wrapped the wire, and when we unwounded it, a profile was created. The locus of the point P was formed, the involute tooth profile. Now, that you may see to satisfy the fundamental law of gearing. How? Because in that case the point of contact or the line of action, this is the line of action because this is the point of contact, and common normal at the point of contact is the line of action. Well, along this the force will be applied by the driving gear to the driven gear. Okay, in this way the force will be applied by the driving gear on the driven gear, and so this is the line of action or the common normal at the point of contact to the two surfaces. And this is the line of center which we have taken as OA and OB, and this is the pitch point. So we see that in the case of involute tooth profile, this line of action always intersects the line of centers at a fixed point which is called the pitch point, and that you may see in this figure. In this figure, this is the pitch circle of the pinion, this is the pitch circle of the pinion, okay, and this is the cylinder which is called the base circle, and this is the circle on which the wire is wound to generate the involute tooth profile. And that wire, you may say, is like this, and when the wire was unwounded, you have formed this profile and this profile. And that you may see that let the wire is wounded in this way, it is passing through A, and then it is tangent to the this base circle, and again it is going in this way. This is the wire. Okay. And now just rotate these two cylinders, this cylinder which is the base circle for this driving gear, and the base circle for the driven gear. On this wire is wounded, and now you are just rotate these two gears in the opposite direction, these two cylinders in the opposite direction, and see the locus of any point on this AB line. AB line is the wire which is tangent on the base circles. Then the locus of this point will generate the two profiles, involute tooth profiles, and thus our line of contact on these two base circles will always lie along this AB, and this line of center will pass through center of the first gear and center of the second gear, and so this O1 O2 is also fixed. If O1 O2 is fixed and this AB is fixed, then the intersection point P will be fixed, and thus the pitch radii O1P and O2P will be fixed, and thus the velocity ratio which you will get will be in the ratio of O1P to O2P. And so in the case of involute tooth profile, you are getting a fixed value of O1P and O2P, and so the velocity ratio will be fixed. You will get uniform velocity ratio. Here we are showing how to generate an involute tooth profile. That you can do by taking a base circle, this as a base circle. Now divide this base circle into number of segments with a smaller angle, this theta, this theta is very small, and join this O to O1 OA1, OA2, OA3, OA4 like that. Then draw tangent line on the base circle from O1, A1, A2, A3 and A4 and like that all along the circumference of the base circle. Well, now we said that when a wire is unwounded, then we get the involute tooth profile. Now when you will unwound the wire, then the wire will be tangent to the base circle. So from the A1 you have drawn a tangent, which is A1 B1. From A0 you have drawn a tangent A0 B0. From A2 you have drawn a tangent A2 B2. Similarly A3 B3, A4 B4 like that. Now along A1 B1 cut a distance AC1 which is equal to arc A1 A0, and thus you are getting a point C1 along A1 B1. Similarly, on the tangent A2 B2 cut a distance A2 C2 which is equal to arc A2 A0. Like that way you will get different points C1, C2, C3, C4. Now join these with the initial point C0, C0, C1, C2, C3, C4 will generate an involute tooth profile, Well, this figure shows a gear tooth with involute tooth profile. This has a pitch circle. Along the pitch circle, the thickness is called the circular thickness, and here gear mesh is shown, is the base circle of the gear, pitch circle of the gear, base circle of the pinion, pitch circle of the pinion passing through the pitch point P, and your pinion is rotating in a clockwise direction and gear is rotating in anti-clockwise direction. So based on which one is the driving gear, which one is the driven gear, you will get the line of action. In this case, the pinion is the driving gear, and so the line of action is from A to this B, which is tangent to the base circle of the gear and pinion and passing through the pitch point. In this figure, you may see the point of contact which is always lying along a line which is tangent on the base circle. This is the base circle of one of the gear and this is the base circle of the another gear. So this dashed line is showing the line of action or the line common normal at point of contact. Now you may see at this point the contact has started and it is ending somewhere here. So point of contact is always lying along this common tangent on the base circles. Now fundamentals of involute tooth profile. The first step in drawing teeth on a pair of mating gears is shown in figure. The center distance O1 and O2 is the sum of the pitch radii to be selected based on the velocity ratio. So the velocity ratio is suppose omega 1 divided by omega 2 or n1 divided by n2, then it will be in the inverse ratio of the pitch diameters. So that will be pitch diameter 2 divided by pitch diameter 1. So knowing the velocity ratio, we can get this d2 and d1, and knowing d2 and d1, you may get the center distance O1 O2. O1 O2 will be equal to D1 plus D2 divided by 2, or pitch radii R1 plus R2. Now, if subscript is written in terms of pinion and gear, then this will be R of the pinion plus R of the gear. This will give you the center distance O1 O2. So, locate the pinion and gear centers O1 and O2, then construct the pitch circles of radii R1 and R2. Now, the pitch circles are this one. This is the pitch circle which is passing through the pitch point. This is the pitch circle. Well, it is represented here, pitch circle. And the pitch circle of the gear is this one. Is the pitch circle of the gear. Okay. Now, these two pitch circles are tangent at the pitch point P. Now, next draw a line AB which is tangent to the pitch circles. We now designate gear 1 as driver, this gear 1 as a driver, and gear 2 as a driven. The meaning is the force will be transmitted from driven gear to the driving gear to the driven gear, the driving gear to the driven gear, and thus, well, the gear 1 is rotating in a anti-clockwise direction with the speed omega 1, and gear 2 is rotating in a clockwise direction with the speed omega 2. Well, now draw a line CD, this CD, passing through pitch point and making angle phi with this AB. AB is tangent on the pitch circles and passing through the pitch point. So, AB and CD both are passing through the pitch point P, which is along the center line joining the centers O1 and O2, and CD is making angle phi with the AB, and this phi is called the pressure angle. Phi is pressure angle. Okay. Now, once you have drawn this CD line, now draw a circle tangent to this CD and from O1 and O2. That circle will be the base circle. Okay. So, tangent to that is this one. This circle is tangent to CD and center O1. Similarly, tangent to CD and center O2 is this one. Okay. Now, these two circles are called base circle. Base circle, from where involute tooth profile will be generated. Now, this CD line is the line which is tangent on the base circle, and so this is the line along which force will be transmitted from driving gear to driven gear, and so this is also called the pressure line or the line of action. It represents the direction in which resultant force acts between the gears. The angle phi is called the pressure angle, and it is usually has values equal to 20 degree or 22.5 degree, 25 degree, or earlier it was used as 14.5 degree, but which is not now used. Now, advantages of involute gear. Variation in center distance does not affect the velocity ratio. That means if center distance O1 and O2 are there, if due to some wear and tear there is slight change in this center distance, then also the involute tooth profile satisfies the fundamental law of gearing. Okay. Now, pressure angle remains constant throughout the engagements, which results in smooth running. Straight teeth of basic rack for involute admit single tools, hence manufacturing becomes simple and cheap. That means rack is something of, this is the involute profile for a rack, and this, with the help of this type of tool, which is a simple rack, basic rack, the involute tooth profile can be generated or can be cut on a blank, and so manufacturing becomes simple and cheap. So, as discussed, the involute tooth profile is generated either by winding a wire on a circle and unwinding it from one end. As shown in this figure, the wire was wound like this, and now we had started unwinding it from this side. So, the locus of this point, that this is a point P, locus of this point was generating the involute profile. Now, the next profile was the cycloidal tooth profile. A cycloid is the curve traced by a point on the circumference of a circle which rolls without slipping on a fixed straight line. That means, if you have a fixed straight line and a circle is there, now this circle is rolling without slipping on this line. Well, then the locus of this point of contact P generates the cycloidal. Now, there are some other cycloidal, like when a circle rolls without slipping on the inside of a fixed circle. That means, this is the fixed circle, and another circle which is inside the fixed circle, and the point of contact is given by this D. Then the curve traced by a point on the circumference of this circle is called hypocycloid. Well, so let the circumference of this circle was touching the fixed circle at this A. Now, when this inner circle rolled, then the trace is this AC, this one. So, this is hypocycloid. Now, when a circle rolls without slipping on the outside of a fixed circle, this was the fixed circle, and another circle is outside the fixed circle. Now, when this circle, outside circle, will roll on the fixed circle without slipping, then the curve traced by a point on the circumference of the outside circle is called the epicycloid. Now, the cycloidal tooth profile is generated at the bottom, which is called the flank, by hypocycloid, and outside, which is called the face, by epicycloid. So, two profiles are there. Along the flank is the hypocycloid, and above, which is called the face, is having epicycloid profile. Here in this figure, the fixed circle is shown in blue color and the hypocycloid green color and epicycloid in another color. And the circles which were rolling, the inside was this one, which generated the hypocycloid, and the outside circle is this one, which has traced the epicycloid. And the cycloidal tooth profile will be a combination of hypocycloid and epicycloid. Now, advantages of cycloidal gears. Cycloidal gears do not have interference. In the case of involute gear, we have interference. Some condition comes when the teeth intersects with each other, and to avoid that we do number of things. But in the case of cycloidal gear, this is not the phenomenon. Cycloidal tooth is generally stronger than an involute tooth owing to spreading flanks in contrast to the radial flanks of an involute tooth profile. In the case of involute tooth profile, at the base you will get more material in comparison to the involute tooth profile. Because of spreading flanks, they have high strength and compact drives are achievable. Cycloidal teeth have longer life since the contact is mostly rolling, which results in low wear. Whereas in the case of involute tooth profile, the contact between gear tooth have both sliding and rolling action. Now, disadvantage of cycloidal gear are, for a pair of cycloidal gears, there is only one theoretically correct center distance for which a constant velocity ratio is obtained. It means the center distance O1 and O2 must be fixed. If there is some slight change in this center distance, then cycloidal profile will not satisfy the fundamental law of gearing and you will not get uniform velocity ratio. The hob of cycloidal gear has curved teeth unlike involute teeth rack. Hence, hob manufacture is difficult and costly. Cycloidal gear will cost more. Now, the gears are used in number of applications like toys and small mechanisms, in which a small low load, low cost and kinematic analysis is required. Appliance gears, long life, low noise and cost, low to moderate load are there. In that cases, both kinematic and some stress analysis is required. For the case of power transmission, long life, high load, speed, in that case kinematic and stress analysis both are required. Aerospace gears, lightweight, moderate to high load, in this case also kinematic and stress analysis are required. Finally, the control gears, in that case also long life, low noise, precision gears are required, and in this case again kinematic and stress analysis are required. Now, there are different types of gears. The first one is the spur gear, which is used to transmit power between two parallel shafts. The shafts are parallel to each other. The used for transmitting power between two parallel shafts. They are simple in construction, easy to manufacture and cost less. They have highest efficiency and excellent precision rating. They are used in high speed and high load application in all types of gear trains and a wide range of velocity ratios. Hence, they find wide applications right from clocks, household gadgets, motorcycles, automobiles and railways to aircraft. One such application is shown in this figure. Internal gear. In the case of external spur gear, the direction of rotation of driving gear and driven gear will be opposite. Like in this case, it is in a clockwise direction, and so another gear which is missed is rotating with the anti-clockwise direction. Now, gears are also used in which one of the gear internal teeth and another has external teeth. It is called the internal gear. In these drives, the meshing pinion and angular speed are running in the same direction. So, both will rotate in a same direction. Their precision rating is fair. They are useful for high load and high speed application with high reduction ratio. Applications of these gears can be seen in planetary gear drives of automobile, automotive transmission, reduction gearboxes of cement mills, step-up drives of windmills. Now, helical gears. In the case of spur gear, we have seen that the teeth was parallel to the axis of the shaft. Now, in the case of helical gear, the teeth are not parallel to the axis of the gear, axis of the shaft. Like you see here, in this case, the gear teeth are parallel to the axis of the shaft, but in the case of bevel helical gear, the teeth are inclined. Well, now in this case also the axis of the shafts will be parallel, and so they are used to transmit power between or the parallel shafts. They have teeth inclined to the axis as shown in this figure. The angle provides more gradual engagement of the teeth during meshing. That means in the case of spur gear, the contact is sudden and all along the width of the teeth. But in the case of helical gear, the gradual contact will be there. First of all, the contact will start at one edge, it will spread, and at the end there will be a point contact. And so initially there will be a point contact which will convert into line contact, and then again at the time of disengagement there will be a point contact. So there is a gradual engagement and disengagement, and so for the same width their teeth are longer than spur gears and have higher load carrying capacity, and they run with lesser noise. Their contact ratio is higher than spur gears, and they operate smoother and quieter than spur gears due to gradual engagement and disengagement. Their precision rating is good. Here also you see the helical gear which is inclined to the axis. Well, they are recommended for very high speeds and loads. Thus, these gears find wide application in automotive gearboxes. Their efficiency is slightly lower than spur gears. The helix angle also introduces axial thrust on the shaft. That means the force which will act will be in this direction, and so it will have two components, the radial component and the axial component. So, in the case of helical gear, an axial force will also come into picture, and to resist that, on the shaft the one of the bearing must be a thrust bearing. Here a gearbox is shown where the helical gears are used. See, and this is the spur gear. Spur gear, these are the helical gears. Now, double helical gear or herringbone gear. We have seen that in the case of helical gear, there is a axial thrust. One of the force which is acting between the gear teeth will be in this direction, and so it will have two components. This is the radial component and the axial component. So, this is the thrust load which is applied on the shaft due to transmission of force by the helical gear. Now, to avoid that, we come to the double helical gear. In this double helical gear, along the width of the gear, two helical profiles are there. Therefore, one of the force will act in this direction, another will act in this direction. Their axial components will be opposite to each other and thus they will nullify, and there will be only the radial component. Well, the shaft is free from any axial force, though their load capacity is very high. Manufacturing difficulty makes them costlier than single helical gear. Their applications are limited to high capacity reduction drives like that of cement mills and crushers. One such figure is shown in this figure. Okay, here you see one of the gear is in this direction. On the same gear, another gear is in this direction. Well, so the axial forces will nullify each other. They are acting in the opposite direction. Now, the spiral gears are also known as crossed helical gears. They have high helix angle and transmit power between two non-intersecting, non-parallel shafts. Now, in this case you see the application is for non-intersecting and non-parallel. That means the shaft of the axes of the shaft are non-parallel and non-intersecting. Okay. They have initially point contact under the conditions of considerable sliding velocities. Finally, gears will have line contact. Hence, they are used for light load and low speed applications such as instruments, sewing machines, etc. Their precision rating is poor. Now, the bevel gear. Now, if you want to transmit power between non-parallel and intersecting shafts, the shafts of the gear are non-parallel and intersecting, then in that case we go for bevel gear. Teeth are formed on conical surface. In the case of your spur gear and helical gear, they were formed on a cylindrical blank, but in this case it is formed on a cone. Okay. So, teeth are formed on a conical surface used to transfer motion between non-parallel and intersecting shaft. They are used for transmitting power between intersecting shafts. They can operate under high speeds and high loads. Their precision rating is fair to good. They are suitable for 1:1 and higher velocity ratios and for right angle meshes to any other angles. Like they may be for the right angle or they may be for more than 90 degree or less than 90 degree. Straight bevel gear, where the teeth are straight, just analogous to the spur gear. For transmitting power between intersecting shafts, they can operate under high speeds and high loads. Their precision rating is fair to good. They are suitable for 1:1 and high velocity ratios and for right angle meshes to any other angle. Their good choice is for right angle drive to particularly low ratios. However, complicated both form and fabrication limits achievement of precision. They should be located at one of the less critical meshes of the train. Wide application of straight bevel drives is in automotive differentials, right angle drives of blenders and conveyors. A typical example is shown in this figure in a differential. Is the rear wheels of an automobile, is the propeller shaft, and between them is this mechanism where these bevel gears are used, because you have to change the direction of the shaft. Propeller shaft has axle in this way and the axle of the wheel is 90 degree to the propeller shaft, and so this bevel gears are used for that case and some other purposes of the differential. Now, spiral bevel gear, here the teeth is not straight but in a spiral form like that, you see, curved, but the axes are non-parallel and intersecting. for transmitting power between intersecting shafts. Because of high spiral tooth, the contact length is more and contact ratio is more. They operate smoother than straight bevel gears and have higher load carrying capacity, but their efficiency is slightly lower than straight bevel gear. Uses of spiral bevel gear is an automobile differential as shown here, the spiral bevel gear. Now hypoid bevel gear, these gears are used for right angle drives in which the axes do not intersect. This permits the lowering of the pinion axis, which is an added advantage in automobile in avoiding hump inside the automobile drive line power transmission. However, the non-intersection introduces a considerable amount of sliding and the drive requires good lubrication to reduce the friction and wear. Their efficiency is lower than other two types of bevel gears. These gears are widely used in current days automobile drive line power transmission. Now, worm gear sets consist of worm gear set, you see, they are used for the non-parallel and non-intersecting. This is the axis of the worm and this is the axis of the worm gear. They are non-parallel and non-intersecting. Like you see, this is the gear and this is the worm. Axis of the worm is this one and axis of the gear is perpendicular to the screen. Worm gear set consists of a helical gear and a power screw used to transmit motion between one parallel and non-intersecting shafts. Now, rack and pinion. This is the rack where the teeth profile is something like this, straight. This is the rack which is shown here. It has this type of teeth and it is meshed with a spur gear. This is the usual spur gear. The axis of the spur gear is this one, and when this spur gear will rotate, this rack will have a linear motion in this way or in this direction. So, to convert the rotary motion into a linear motion, this rack and pinion arrangement is used. Here a lathe carriage drive mechanism is showing rack and pinion arrangement. Here a rack and somewhere here will be the pinion. Here also is the rack. When you will give rotation of this wheel, a pinion is there and with the rotation this will move up and down. So, radial drilling machine spindle movement with rack and pinion arrangement. So, with this the introduction of gears is completed. Now, we will study in our next class in detail the spur gear and design of spur gear. Thank you.